Right, so June 2010, okay, so the string is slack initially in the question, okay, if we look at it here, so there's the string slack and distance there is 0.3 meters, and then it's given a push in this direction of speed 8 meters per second, so across there in that sort of direction, which is perpendicular to this line 0.3. So if it pushes that way, it'll just keep going that way, okay? It'll keep going that way until the string becomes taut, and then there's a jerk reaction then with the particles. So ultimately we get a situation like this, okay, occurring when the string becomes taut. So Q has gone across the page there, so to speak, going at the speed of 8 meters per second. All right, and the string now is taut, that's 0.6, of course we know that's 0.3. What that will allow us to do is to work out this angle here, which is kind of important, okay, because ideally with the speed of 8 there, we'd like to resolve that speed parallel to the string, along the string and perpendicular to it. So if I've got this angle, it's going to help me because that angle, if you think about it, is going to be the same as this angle here. Yeah, because opposite angles are vertical, opposite angles are equal. So I can then work out what that speed component of 8 is along the string, and of course perpendicular to the string, okay, which is obviously very important when it comes to impulsive tension work. Now theta, okay, we can work that out straight away, because if you look at the triangle that's formed here, opposite then the angle there, we've got 0.3, and of course then that's the hypotenuse. So we know what sine theta is. Sine theta will be opposite over hypotenuse, okay, 0.3 over 0.6. So that means then sine theta is a half, so theta is 30 degrees. Okay, so we know what theta is. We know it's 30 degrees. So when we resolve that speed component there along the string, of course theta, this angle here along the string, will be cos then, when it'll be 8 cos 30 here, okay, and it'll be 8 sine 30 perpendicular to the string. So that's the component of the speed along the string perpendicular to the spring just before the string jerks, right? So just as that string becomes taut, we've got our components here. So what I do now, I've got my before situation, so I'm going to fill these in. Okay, then the after situation, all right? Now after, if you think about it, particle P is going to move, isn't it? But particle P will move along the string, okay, because the string it's attached to is what is going to be pulling it, and of course the string is already in this taut direction, isn't it? The string is taut in this direction, so immediately afterwards that string is going to just give this a pull, so it's going to be going this way, so there'll be only speed particle P going this way, there'll be no component going perpendicular to the string, okay? And we're talking about immediately afterwards, literally straight afterwards, okay? Nanoseconds afterwards, because of course, you know, a good few seconds after that, it's going to be, you know, the string's going to change direction and so on, right? So will particle P. But particle P will follow that string. So as soon as the string becomes taut and there's a jerk reaction and it starts to move, it'll go in the direction of that string. So if we call that speed U, and what's good, of course, then that component there is going to be the same as the component here. Because the string is taut, they'll be moving at the same speed horizontally. And of course, then we'll call that maybe V, all right, which is perpendicular to it. So what I can do then is apply the conservation of momentum, okay? So momentum is conserved simply because no momentum is lost in the whole system. If you think about it, that's traveling along nicely, okay, and then the string becomes taut, and there's a jerk which pulls this back, okay, pulls this back, so this is going to lose speed, but the jerk on the string actually pulls then P forwards, so even though this loses speed, that gains speed, so this loses momentum, this will gain momentum, so overall there's no loss of momentum, okay. So if we look along the string, okay, so if we resolve along the string, beforehand, okay, the momentum, well, there's no momentum for that, and we've got momentum here, so we've got 8 cos 30, which is the speed, times then the mass, or mass times speed, so we can do it that way if you want, okay, mass times speed is that, along the string, equals there, afterwards, well, we've got mass times the speed there, which is u, plus then the mass of that times u. So remember now we're looking at the total momentum of the whole system. So the total momentum afterwards, going along the string, will be mass times this and then mass times this added together. That's the total momentum combined, will equal the total momentum combined before, which is just this times 5. Okay, so you've got that there. So now be 40 cos 30 equals 8 u's, then you can get u out then. Be 40 cos 30, okay, divide by 8. Okay, so we get that out to be 5 root 3 over 2. Okay, so that's what we've got there. Now what we do then, of course, is resolve perpendicular, okay, or we apply the conservation of momentum perpendicular to the string. Okay, so if we go perpendicular to the string, then the momentum after will equal the momentum before. So let's look at the momentum before. When you've got 5 is the mass and you've got 8 sine 30 going perpendicular to the string, so that'll be 5 times 8 sine 30, okay, and then that will equal then afterwards, well, you've just got this, haven't you? So you've just got v and the mass, so mass times v, okay, and there's no movement perpendicular to the string there, of course. So that will be then 5 times 8 sine 30 equals v, so you get v out to be 5 times 8 sine 30, and then divide by 5 is 4. Okay, so v will be 4. So in our diagram there, now we can actually work out now what the speed of q is. So we know what the speed of p is. Speed of p is just going to be that afterwards. We could say like speed of p is 5 root 3 over 2 meters per second. Speed of v then will be this, the combination of this basically. So we just use Pythagoras. So speed of q will be this squared plus then 4 squared, and of course then square rooted. So if I do that on my calculator, I get out 5.89, okay, meters per second. All right, and there's the speed there. Now, to get the impulsive tension, okay, to work out the impulsive tension in the string, all I need to consider is the change of momentum. So the impulsive tension in the string, we can just look at the change of momentum of one of the particles. Because if you think about it, how particles change momentum defines what tension there is in that string. So if I would focus on particle P, because P to start with didn't have any momentum. Okay, so that makes it easier. And we know, of course, the momentum at the end. So how it's changed momentum defines what the string is doing, yeah? That impulsive tension in the string. So remember, impulsive tension is change of momentum. So if we focus on P, okay, you can focus on Q if you want, but P will be a lot easier. So the momentum afterwards will be, well, the mass is that, and the velocity is that. So 3 times 5 root 3 over 2. Take away then 3, of course, times 0. So there's our answer there. So it'll be 15 root 3 over 2 newtons seconds. Okay, and we're done.